In this second mini lecture, we will look at the aircraft response to longitudinal gust through a more detailed example. So let's first see what is longitudinal gust. A longitudinal gust is a serious problem. They are usually under the title of microbursts or wind shear. Microbursts are normally associated with thunderstorm activity in the atmosphere. In the present analysis, we are looking at the violent downdraughts. And you can see from this picture, we have a downward flow, and we call it is downdraught. And you can see there is a stagnation area on the ground because once that's a head-on collision, and that part we call it stagnation area. And then the wind will be guided towards the left branch and the right branch, and the left branch is denoted by A and the right branch is denoted by B. Okay, so now assume an aircraft is flying from point A to point B. What will happen? Can you imagine? So from A to the stagnation point, the aircraft will have head-on wind, so the wind is blowing towards the aircraft. And if the aircraft is flying from the stagnation area to point B, so there is a tailwind. So let's have it in more detail. So from A to stagnation, the aircraft will have headwind, and from stagnation to point B, there will be tailwind for the aircraft. And you can see there is an alternation of the wind speed, so that will change the aircraft true airspeed significantly. Is that right? Okay, so let's see. From A to stagnation, headwind. There's a headwind, for example, it's 20 knots. And from stagnation to B, that's a tailwind. And again, it's, for example, it's 20 knots. So in total, when the aircraft is flying across A and B, there's a total loss of 40 knots of true airspeed. So you see, this is very significant velocity loss. And if there's a velocity loss, can you imagine what will happen? The aircraft will lose lift, and then it will go down. So it will lose height also. And if it loses height, is that a problem? Especially when it's during takeoff and landing, so it will hit the ground. When it's very close to the ground, that's a disaster. Okay, so now let's move forward, but by keeping this in mind, this scenario in mind. So it is disasters near airfield where speeds tends to be lower, especially during takeoff and landing. So now let's move on. And so having that scenario in our mind, now let's conclude a simplified model for phugoid mode. How do we build up a simplified model for the phugoid mode? And these are the description. Once the aircraft enters a downdraught, there is a rapid loss of lift because lift is proportional to the true airspeed, and we have significant loss of true airspeed. Therefore, longitudinal disturbance should be experienced because there is a velocity loss, and then that will cause a longitudinal disturbance. Any SPPO will die away very quickly, but the phugoid mode is still there. So since there is a longitudinal disturbance, it will cause longitudinal instabilities. And we know for the longitudinal instability, we have the short period pitching oscillation and the phugoid mode. And as indicated here, the phugoid, the SPPO short period oscillation will die away, will be damped out very quickly. But because the phugoid mode is still there, we need to look at this. And can you remember what is phugoid mode? And how did we do the analysis of the fuel-going mode? And still through a simplified model, that's a Lanchester model, by assuming there's an energy conservation of the potential energy and the kinetic energy. And you can see if there is kinetic energy change loss, and then the potential energy will also loss. That will cause the height to reduce. Okay, so assume the change in true airspeed is delta V or minus U. U is all in here. We assume U is positive. That's why we add a negative sign there. So the true airspeed is decreasing because the aircraft is flying from headwind to tailwind. Now we can carry out very simple analysis based on the loss of height. Above the ground, delta H, the target now in this simplified model, we want to calculate delta H and the change in the kinetic energy. The potential energy change will be mg times delta H. Is that right? So that's a potential energy change because usually we assume there is energy conservation in the fuel-going mode. So we have this. The left-hand side is potential energy change. On the right-hand side is the kinetic energy change. So the height loss is delta V squared divided by 2g. Okay. So now let's get some numbers. If u is 40 knots, so there is a decrease of velocity of 40 knots, and the original true airspeed is 150 knots, and that's about 1/15, right? So it's about 30%. And then the height change, according to that analysis, simplified analysis, delta H is 140 meters. So you see it's a very big number. For light aircraft at even lower true airspeed, this could be catastrophic. So you see the problem. And according to the current simplified model for the fuel-going mode, actually this analysis follows what we did for the Lanchester analysis when we discussed the fuel-going mode in the earlier chapter. Although the analysis is a very simple one, it shows that the sudden acquisition of a tailwind component will cause a rapid loss of lift because there is a switch of from headwind to tailwind. Then that will cause velocity change, velocity reduction. And a fuel-going mode will be superimposed on the now steeper descending flight path curve. The pilot must apply full power, so accelerate, otherwise a stall could ensure because the speed is also lost. Even if a stall is avoided, the aircraft might still hit the ground because there is a loss of lift and the aircraft will lose height. So this should be avoided. Okay, now here is an example, detailed example. This phenomenon can also be judged as problematic on takeoff. Just now was landing, now we are looking at taking off. The sudden tailwind component just after liftoff could bring the aircraft to well below its calculated rotation speed, and fatal accidents have occurred under just these conditions. And for example, in 1982, a Pan American Boeing 727 takeoff in a microburst from New Orleans airport experienced a catastrophic loss of height when about 160 feet above the ground and about 8,000 feet from the start of its takeoff run. It hit the ground after another 4,000 feet of progress. You see, and the picture is showing here, and we can see, and this is a more artistic view, I would say, and you can see the downflow, downdraught, and then it will split up into the headwind and the tailwind for the aircraft, and solid line we can see is the path of the aircraft. So we can see the aircraft lift off in headwind, and then once it enters the downwind, tailwind, and it start losing height and then hit the ground. So you can see the how this happens for a taking off aircraft, and so especially when the the regulation should ask the pilots or the airline to avoid operating under this downdraught condition. Okay, so this is very a big problem, should be avoided. I hope it's clear for the current analysis for the aircraft response to a longitudinal gust. So from headwind to tailwind, and that will cause instabilities, longitudinal instabilities. Since as PPO, it will be damped out very quickly, and our focus is placed on the phugoid. Okay, so let's finish this mini lecture.